Hello, my name is Ignacio Matías, and I want to present the work entitled Highly Sensitive Hollow Core Fiber Optic Sensor using a ring laser for measuring material thermal expansion. This work has been possible due to the collaboration of the Electrical, Electronic and Communication Engineering Department and the Institute of Smart Cities, both from the Pública University of Navarra in Spain and the Department of Telecommunication and Electronics in the Pinar del Río University, Cuba. So in this work, a very high sensitivity material thermal expansion sensor is going to be present. The setup, you can see here, the experimental setup consists of an interferometric fiber sensor and that one, and an erbium-doped fiber ring laser as a light source. The pool laser is coupled into a erbium-doped fiber of a length of 2 meters and by using a wavelength division multiplexer device. The laser includes one ring cavity in a reflective way. This is the light is going that sensor and back in a reflective way, and in a single mode fiber ending in a coupler, in a 50-50 coupler, just to complete the ring. Also, part of the signal, instead of going to the feedback of the ring, go to the optical spectrum analyzer in order to see the spectrum of the sensor and to detect the variation with temperature. This sensor head is located onto the a metal plate. In our case, we use aluminum and steel, whose thermal expansion is understood. This sensor head consists of a three section of fibers, a different type of fibers. First of all, a single mode fiber, then a hollow core fiber with an outer diameter of 245 micron and in a diameter of 100 micron, and a no core solid fiber of also about 100 micron. This no core fiber and the single mode fiber is there are separated at like 35 micron. This gap, you can see here better this gap in this picture. This is the sensor head, and this is some details of the sensor head. The interferometric signal coming from this sensor head is obtained in the optical spectrum analyzer, and you can see here is a plot of temperature. The wavelength displacement when varying the temperature in a step of 1 degree centigrade, it's possible to see in these two graphs. In the upper one, this is in the case of steel, and here in the bottom in the case of aluminum. You can see in this step that this is a very repetitive signal from the sensor. The sensitivities of the thermal expansion sensor, you can see here in the case of aluminum and steel. In aluminum case is almost 40 nanometers per degree centigrade, and in the case of steel is about 6 nanometers per degree centigrade. That is in accordance with the thermal expansion coefficient. The aluminum has a higher thermal expansion coefficient than the steel. And you can see here, but just knowing the coefficient of the metal, in this case, it is possible also to know the temperature at what this metal is. In this case, the resolution we could get is something like 0.026 degrees centigrade per nanometer. That is a very high sensitive temperature sensor, actually almost 2 degrees to order of magnitude better than a fiber magnetic. And just to conclude, a highly sensitive expansive sensor has been obtained using a combination of single mode, hollow core, and no core fiber, and a displacement of 1 nanometer in the wavelength of the sensor response corresponds to a change of less than 0.026 degrees have been obtained, which is a semi-high sensitive sensor, 2 orders of magnitude higher respect to fiber magnetic, for example. Thank you very much.